So now we're going to talk about angle of twist. And statically indeterminate bars and torsion. And what we're talking about is if you have a delicious piece of summer sausage and you apply a torque this way and a torque this way, before the deformation, you could draw a line across it like this with a marker. And after you apply that torque, that line is going to do this. That's exaggerated, but and this angle here, that's the Greek letter phi, and that's what's called the angle of twist. Everybody follow what I'm talking about here? Try to draw this straighter. Okay, so for this calculation, I want you to look at the form of the elongation of members in tension. So look at the basic form of delta for a member in tension. So we got, if we're just looking at the constant internal tension form, delta is equal to T times L over E times A. Okay, and let's think about what each of these multiples represent. So T is the internal load. L is the length. E is a material stiffness against the internal load. Let's say material stiffness resisting the internal load. And A is a geometric resistance to that internal load. Okay, so that's kind of a general way to think about each of these things. And if you think about those that way, it'll help you remember the form for the angle of twist for torque. This angle of twist has the same form, same basic form. Phi is equal to, when we're talking about angle of twist, what's the internal load that matters? Torque. So fancy T. And then length is still length. Then we're talking about the material stiffness that resists shear stress. I'm going to call that G, and I'll give that to you in a second. But that G is just, just like E is the element of the stiffness matrix that, so you can go between stress and strain. G is the shear element of the stiffness matrix that lets you go from stress to strain. And then when you're talking about twisting, what's the geometric resistance to torque? You remember? When we were talking about shear stress due to torque. It wasn't it wasn't area. Area resists like a tension or a compression. It wasn't the area moment of inertia, that resists bending. It's a third one. I sub P. Polar moment of inertia.
Oh yeah, of course.
If you go back, you can see that that's all based on geometry, and it gives you a resistance based on the geometry to a torque. And then that G is equal to E over 2 times the quantity 1 plus nu. That's shear element of the stiffness matrix. We've used the compliance matrix more than we've used the stiffness matrix. And if you remember, the compliance matrix has shear elements of 2 times the quantity 1 plus nu over E. Well, stiffness is the inverse of that, so you're just going to get the reciprocal. Okay, so just notice that there's that relationship between the macroscopic deformation in torque and the macroscopic deformation in tension compression. And then there's the two other forms too. So here are all three formulas for angle of twist. The first one says that the angle of twist is equal to the integral from 0 to L of the torque dx over GIP. Oh, you can also remember that because GIP is a funny thing to say. Yeah. Yeah. That's probably an easier way to remember it than the thing about. Yeah. Okay, so that's the definition. And then there's the one for piecewise constant internal torques. And that's just the sum from I equals 1 to N of T sub I, L sub I over G, I sub P. And I guess you could have geometric changes as you go along, so this could also be an I. You know, you could have something that has different diameter cylinders as you go across, a thicker part here and a thinner part here. And then the third one is for all these values being constant. That's the one that we just came up with. So phi is equal to internal torque times length over g I sub d. When do you use this one? Hopefully never. But when do you need that? Yeah, so if there's continuous changes of any kind. And then this one is for piecewise constant. And you have to use that form if it's piecewise constant for any one of these three that can vary piece by piece. We're not going to have anywhere the material changes from one part to another, although I guess you could. You know, you could have something that's like steel at one point and then wood at the other point, and then you would make that change there. I'm still not writing an I there, though. Am I? No. And then this one if everything's constant. Any questions about that? Great. So let's say that we have a bar connected rigidly to the wall and 700 Newton meter torque applied at the right end. And let's say that the G value is equal to 80 times 10 to the 9th pascals. And the polar moment of inertia is 1.57 times 10 to the minus 8 meters to the 4th. And we want to calculate the angle of twist along this whole thing. The first thing we have to do is calculate the internal torque. In this case, we have a reaction torque at the wall. I'll call that fancy T sub R. And then we have the external torque of 700 Newton meters. And the rotational equation about the x-axis says fancy T sub R is equal to negative 700 Newton meters. And then do a cut. This one cut is valid for every x. I give a length, 0.6 meters. So this is valid for every x between 0 and 0.6. So at the cut, the free body diagram looks like this. You have 700 Newton meters this way, and an internal torque T going that way. And so the x moment equation says negative 700 plus the internal torque is equal to 0. So that internal torque is equal to positive 700. You don't have to go through all that if you can just look at that and see that it's, you know, and if you can't now, you will by the time you do a few of these problems. But in more complicated problems, remember that you always can just go back to calculating the external loads, do the cuts, calculate the internal loads, and those internal loads are what we're looking for. Since this internal torque is uniform over the whole thing, our angle of twist is just going to use this formula, T times length over G I sub P. And so that's 700 times 0.6 divided by 80 times 10 to the 9. And then I sub P, 1.57 times 10 to the minus 8. And you get a total value of 0.334 radians. Okay, so how much is 0.334 radians? What kind of angle is that? How much is a radian about? There's 2 pi radians and 360 degrees, so each one is somewhere around 60 degrees, right? So this is about 20 degrees. So that's a pretty big angle of twist. And you know, that's not a super huge torque, but that's a bar that's almost a meter long. You know, it's what, this long. And so the longer this thing gets, the bigger that angle of twist could be. You could apply, if you had something that was 6 miles long and you applied a pretty small torque to the end, you could still get that thing to go all the way around multiple times and still never have very big strains. Okay. Yep. Mm-hmm. Yeah. I don't know, but so that's a good question. I don't really know what happens if you deform something in torsion until it breaks. I don't know what kind of shape it takes. But I do want to point out that we're still assuming that this is, so even though we're talking about twisting this thing 20 degrees, we're still assuming that this is in its linear elastic range. Okay, so if you had something that was 5 miles long and you torque the end of it, you'd get this thing to rotate a full time around or whatever. That's a huge deformation, it seems like, macroscopically. But each individual, like, local deformation is still really small because all of that deformation is happening over 5 miles. And so even though you have a big macroscopic deformation, you have really small strains. That means you have small stresses. And this is still totally in that linear range of, we're still not talking about permanent deformations. If you let go of it, it would happily go right back, you know. And you've seen that happen, or maybe you've seen that happen with like torsion springs. It's sort of the same idea. You know, a torsion spring is like, they used to use these in watches and clocks before electricity took all the fun out of timing stuff. But you have a hairspring that's, you know, goes around and around and around, and this thing will oscillate back and, you have a, you have this connected to, it's not really a mass, but you can think of it as a mass like that. This thing will oscillate over a big range, but that's not saying that any part of this spring is undergoing a big deformation. It's just every little part of this super long spring is deforming a tiny little bit. And if you integrate it over the whole length, it comes out to be a big deformation. But it still stays in its linear range. It still obeys Hooke's law like any spring does. So, any other questions about that? Yes. Yes. The thickness of the bar goes into I sub p. And what's the formula for I sub p for a round? We only did it for a round cross section, but I sub p is equal to, I think, pi over 2 times the radius to the 4th. I think that's what the formula was. Yeah. And so, yeah, your intuition says if this thing was, so if this bar, this 0.6 meter long bar was, and let's say it's steel or copper, it's some kind of metal. If its cross section looked like that, and you applied this fairly small torque to it, even though 0.6 meters is pretty long, you wouldn't get any twist at all, basically. And the way that would happen is you'd get a much bigger value of that polar moment of inertia. And so then in this formula, you'd be dividing by something big, and you'd end up with a much smaller value of the angular twist. Any other questions? Okay, so to use this in a statically indeterminate system, so let's say that we have a wall here and a wall here, and those are fixed, those aren't going to move. And we have a bar in between them with fixed joints at both ends. And let's say that somewhere in here, we apply an external torque of 1,000 Newton meters. So let's say that this is 3 meters. This is 1 meter. And let's say that Young's modulus is 200 times 10 to the 9th. That's steel. Poisson's ratio now we need. And let's say that that's 0.25. And let's say that this has a circular cross section of 1 centimeter. What are the external loads? Okay, so this is going to be statically indeterminate because we're going to have one useful equation from Newton's laws. That's going to be the x moment equation. Okay. So that's one equation, but we're going to have a torque here and a torque here. So two variables, one equation. Those two torques together have to counteract this. Okay, so probably we're going to get each of them applying a torque in the opposite direction, and those have to add up to 1,000. Intuitively, do you have a sense of which of these two torques is going to have a bigger absolute value? Yeah, this one's going to have a bigger absolute value because it's closer to the load. And so we're going to first use statics to get that first equation that's going to tell us this plus this is equal and opposite to this. And then we're going to do our cuts, figure out the internal torque on this section and the internal torque on this section. Then we're going to calculate the angle of twist based on these variable values for internal torques. And then we're going to say, well, what's the total angle of twist as you go from here to here? It has to be 0. It can be something in between. You know, like if you drew a point with marker here and then applied the torque, that point with the marker on it would move. But here, that's fixed to the wall. Here, it's fixed to the wall. So the total angle of twist is going to have to be 0. And I think it looked like this. So there was this bar between these two fixed supports. And there was a torque one way or the other of, I think it was 4,000. Opposite way. Oh, 1,000? So 1,000 Newton meters. And this was 3 meters. And that was 1 meter. And it was a circular cross section with a radius of 1 centimeter. What are the external loads? Okay, so first we need to do the statics, and in general you'll look at a problem and you know, for a complicated problem you don't know from just looking at it whether it's statically determinate or not. You just come up with the equations, and if you have enough equations you're done, and if you don't you need to go on and use the deformation stuff. So first the statics. So Freebody diagram. The only stuff going on is moments, couples about the x-axis. So we have this 1,000 Newton meter torque here. And then we have reaction torques at these two ends. I'll call this torque A and torque B. And the moment equation about the x-axis says torque A plus torque B plus 1,000 is equal to 0, or these two together are equal to negative 1,000. So that's one useful equation, two variables. So we know we're going to have to find more equations, and we'll just call that equation star and move on. So now what we have to do is calculate the internal torques. How many cuts do we have to make in this? 2, because we have the point torque. So our first cut is valid for x's between 0 and 3. We have this torque TA, and we haven't gotten to this 1,000 Newton meter torque yet. And then we have the internal torque. So the moment equation about the x-axis says TA plus T is equal to 0. Or in other words, whatever TA is, the internal torque there is the opposite. Okay, so this is valid only for x values between 0 and 3. And then the second cut is for x's between 3 and 4. This time we do have that 1,000 Newton meter torque. And we do have this TA still. We just haven't gone all the way to the other external torque, the other reaction torque. And so we have the internal torque T. And the moment equation about the x-axis says TA plus 1,000 plus T is equal to 0. So this time T is equal to negative TA minus 1,000. And that's valid for x values between 3 and 4. And now we want to use these expressions for the internal torque to calculate the angle of twist that we get for the entire beam. By the way, so we have this expression T. Why did we have to go through all this to come up with T as a function of TA? Why didn't we just leave that as a variable T? Yeah, exactly. I mean, in a way, you can think of these as more constrained equations. We started out with the variables TA, T, and TB. We can't do anything about those, but we don't want to bring in any more variables or we're going to need even more equations. And that's why we want to express everything that we have here in terms of the variables we already have, you know. And now the final restriction says, since this is a fixed support, we don't know what the angle of twist is at any of these points in between the two supports, but we know that there's no angle of twist between this and this point, okay? It can be twisted here, anywhere in between, but it has to go back by the time it gets here to that starting twist, because those can't slide on the wall. Okay, so the total angle of twist over the whole length is 0. And we have piecewise constant internal torque, so we're going to use this formula that says the angle of twist is equal to the torque, the internal torque on the first part, times the length of the first part over G times I sub P. and then plus the internal torque on the second part times the length on the second part divided by G times I sub P. I said also when I set this problem up that this is a kind of steel that has a Young's modulus of 200 times 10 to the 9 pascals and a Poisson's ratio of 0.25. We can use those to calculate G. G is equal to E over 2 times the quantity 1 plus nu. So that's 200 times 10 to the 9th divided by 2.5. What do you get for that? Eight times 10 to the 8th. Oh, yeah, right. 8.0 times 10 to the 10th, right. And that's still in pascals. And then we need the polar moment of inertia. For a circular cross section, that's pi over 2 times radius to the 4th. So pi over 2 times 0.01 to the 4th. So 1.57 times 10 to the minus 8. Yes. I got it going on today. I got one right in dynamics. This is meters to the 4th. So the total angle of twist is negative TA times 3 divided, oh, that's not even going to matter anyways. None of this stuff is going to matter. Nothing really matters. Because this is all going to cancel out. The 3 is going to matter, and the torques are going to matter, but not the... plus negative TA minus 1,000 times 1 divided by G I sub P. And the reason those won't matter is because we have 0 angle of twist. So we can multiply both sides by G times I sub P. And so you get minus 4 P sub A is equal to positive 1,000. And so T sub A is equal to negative 250 Newton meters. Now plug that back into equation star, the thing we got from the statics. That's a terrible star. And you get negative 250 plus TB is equal to negative 1,000. So T sub B is equal to negative 750. And so the external load that's closer to the, the reaction load that's closer to the applied load has to take up more of that load. And that's, you see that always. Any questions about that? That's a good question. So, well, the way you would do that is, so we know the internal torques everywhere. So if you plotted this out, here's 3, here's 4. We know that we have a internal torque of positive 250 on the first part. And on the second part, we have 250, so minus 750. Okay, so that's what a graph of the internal torques looks like. And so you'd have to, decide whether you want to calculate the angle of, the angle of twist. So it won't matter either way. Okay, so the angle of twist is the internal torque times the length divided by G I sub P. And we're just going to do it over those first 3 meters. So this is going to be 250 times the length of 3 divided by 8 times 10 to the 10th times 1.57 times 10 to the 8th minus 8th. And could someone calculate that? .5997 0.597 radians, which is a pretty big angle. But so what that says is it goes through an angle of like 35 degrees or something. 34.2. Yeah. 34.2 degrees is the angle of twist right where that external load is applied. And then it goes back to an angle of twist of 0 at the 2 attachment points. So then to choose, you always just start from the left. Yeah, if you started from the right, you'd have to just think about the signs more, but you could do that too. I would just always go from the left. I mean, you could figure out how the signs work if you thought about it a little, but I would just always go from the left, and then you don't really have to think about it. Any other questions? Okay, let's stop. So test on Friday.